Okay, hello and welcome to the second video on general computer programming or coding. So on this video, we're going to talk about more of the nuts and bolts of computers and how they actually work, because a lot of people use a computer every day and never really understand what's going on and why. Okay, first of all, with computers, the problems that computers can tackle were really important early on. When the first computers were being built, they needed to really try to understand what problems a computer could solve. And they determined this with the term computable. So if a problem is computable, that means a set of steps can be used to solve it. And it's really, some of the problems are extremely complex and, way over my head. But Alan Turing was the name of the guy that did this initial work, and he talked about what makes a problem computable step by step. So I've got a few simple examples that'll help us begin to understand computability, but the most challenging computable problems are way beyond the scope of this lecture, and are tackled by some of the greatest minds of our time. But here's an example of a computable math problem. So this is a math problem we can solve with steps. And let's think about it. So we want to solve for x equals some integer. And here's our relationship. And we want to say x equals something. So the way we could solve this by steps. So step one, I'm going to use what's called the addition property of equality. And that's going to allow me to add 5 to each side. So the result's going to look like this. And step two is going to be to divide both, or I'm sorry, subtract x from both sides. So that's going to look like this. 2x minus x is x. X minus 10 minus x is just 10. So here we have it. We have solved the problem. It is computable. We use these two steps to get to where we needed to be. So we could create a program that replicated those steps. Now, of course, you couldn't give instructions this simple in plain language to a computer, at least not most computers. You would have to, encode that in some language the computer understands. But nonetheless, it is an example of a computable math problem. So let's look at another one. So here's another math problem, and our task is the same. We want to get it equal to some integer. So the first thing we'll do, we'll just try using rules of algebra to do this. Let's see, if I want to get x by itself, I need to add 5 to each side. And that's going to look like this. 2x equals 3y. And then 7 plus 5 is going to be 12. And so now I need to divide both sides by 2. So that'll be step 2. So that's the division property of equality. And here's where we run into a real problem, because there's no algebra we can do to this right side of the equation to turn it into an integer. We just have to know what y is. We don't have enough information. So this is a non-solvable or non-computable math problem. There's just no amount of steps that would make it work. We've run into a roadblock that's completely unpassable. And so it's a non-computable problem. Let's look at, all right, so here's an example of a computable real-world problem, one we can solve with steps. So step one for solving this problem, so the problem is we imagine a ball is dropped from 200 feet high, and we want to know its height after 2.1 seconds. Now that will have an exact answer and a predictable answer. There are small things that could vary, like temperature could change it ever so slightly, air density, wind speed, but we'll just ignore all that. We'll imagine it's in a vacuum in a perfect situation. What would its height be after 2.1 seconds? Well, the first step is to develop an equation, and that's going to be y, where y is the height, equals -16 times x, or x is the time that has passed, squared plus 200. And that comes from elementary physics. That's the work of Sir Isaac Newton that developed that equation. And step 2 is going to be to plug in x equals 2.1, which is what the number we're concerned about. So that comes from the problem itself, which gives us this: y equals -16 times 2.1 squared plus 200. And then the final step is to solve for y, and we get y equals 129.44 feet. So after 2.1 seconds, starting at 200 feet, it will be at 129.44 feet. And the nuance of the problem aside, that's an example of a computable real-world problem, one we can work through with steps. An example of a real-world problem we can't work through with steps, and the classic one of these is Turing's halting problem, which is, again, very complex and super sophisticated. Feel free to watch a YouTube video on that. It is kind of interesting, but you'll probably have trouble following it if you're not a physicist or something. But anyway, here's one. What is the exact velocity and position of a particle? So there's a law of physics called the uncertainty principle that says the more precisely you know the velocity of a particle, the less precisely you know its position, and vice versa. And so there's a hard limit on how precisely we can know its velocity and position. So before, when we drew that formula, so this step right here, we were able to solve that problem. But when we try step 1 here, we try to get a formula to allow us to do that. No such formula exists. It's impossible. So this is an example of a non-computable real-world problem. There is no algorithm, no step-by-step-by-step solution to this ever. And in fact, this is an unknowable thing in our universe. It's pretty interesting. Okay, so a computable programming problem. So can you create a program that takes a user's height and weight and computes their BMI? Well, yes, of course we can. We did this yesterday, in fact. So the step 1 would be to get the info from the user. Step 2 would be to convert units. You remember that if you saw that first video, we had to convert the units. And step 3 was make the calculation, which is a pretty simple formula. And then step 4 would be to output to the user. So that's a pretty simple computer problem here. Now, non-computable problems are a little more difficult. Okay, so here's an example of a non-computable programming problem. So create a function that compresses any kind of data into the shortest possible description of that data. So there's no way to do this in a step-by-step process. There would always be room for more compression, up to the point where you would never list enough steps to make that possible. So we could never do this. This is a non-computable problem. And so computable problems can be solved with step-by-step instructions. Non-computable problems can't. And that was very important to understand for early computer scientists that developed the computers we use today. So how does computer logic work? Well, basically, you're going to give the computer information, and you can do this a bunch of different ways. You can type something on the keyboard and hit enter. You can move the mouse around and click on something. That's an example of an input. But there were many ways to do this in earlier computers. You remember we talked about the punch cards that old computers would take. That was an example of an input. Some of the other earlier computers had strange one-off input devices that didn't really catch on. But basically, anything you communicate information to the computer with is an input device. And then the CPU is going to do something with that information as defined by its software. And remember, its software is that set of step-by-step instructions that tells it what to do. And then it'll give you some output. That output might be something that shows up on the monitor. It might be a sound that plays through the speakers. Could be a bunch of different things. You know, if you're using a medical device, it might be, you know, some vibration that tells the person something's going on or whatever. Many examples of output exist, but the computer receives information, processes it, and then spits it back out to you in some way. And these are the most common here, but there again are many, many other ways computers can communicate. Alexa's input is by voice, for example, and then its output is also voice through the speakers. So this information you're talking about, how do you encode it? What kind of information is the computer actually receiving? Well, it's not language like the information we typically get. Instead, it's usually binary numbers. In other words, just zeros and ones. So zeros and ones are the binary number system. It only has two symbols, a zero and a one, an on or an off. And believe it or not, it's the way your nervous system uh, communicates with your brain. You know, so your nerves can only send one of two signals to your brain, on or off. And based on that big long string of on or offs, our brain processes that and turns it into the world we see and hear and feel and touch. You know, like for example, if I'm not touching anything, the uh, nerves at the end of my finger are communicating that to me with zeros. You're not touching anything. You're not touching anything. But if I were to put pressure on the desk here, now my nerves are sending a one, one, one. You're touching something. You're touching something, and so on. You guys get the idea. But computers use the same process basically, zeros and ones. And it stores these in memory registers, and it uses those registers to manipulate the data or do whatever task we have challenged it to do, to convert the data in whatever way is defined by its program. Computers only do what they're programmed to do. They're not sentient like us. They don't make a decision to do something. They're only It's only possible that they do what their program defines. At least so far. In the future, that might not be the case. Who knows? So what are binary numbers and how do they work? Well, first of all, in order to explain binary numbers, I think you need to understand some elements of our number system. So if I write a number in our current number, so this is base 10, which is what we use. If I write 3,267.5672, so if I were to write this number, you know what this means. This is 3,267 and then 5,672 ten thousandths. So the reason why we know that is because we have this decimal, which is called the radix point. It tells us that's everything to the right of that is fractional, and everything to the left of that is greater than 1. So this is a fractional part, this is a whole number part, and the decimal gives us that information. But as far as the individual powers of 10 go, so this is not just 7, but it's 7 times 10 to the 0 power. Anything to the 0 power is 1, by the way. And this 6, and it's because it's base 10. So every successive column to the left is going to be a higher power of 10. So this 6 isn't just 6, it's 6 times 10 to the first power, or 60. And this 2 isn't just 2, it's 2 times 10 squared. So 0, 1, 2 powers of 10 here, which is 200. And then this 3 isn't just 3, it's really 3 times 10 to the third power, or 3,000. And then the ones to the right of the decimal work the opposite. That isn't just 5, that's 5 times 10 to the negative 1. And then the 6 is 6 times 10 to the negative 2. And then 7 times 10 to the negative 3. I haven't really left myself enough space here. Let me fix that. Okay. There we go. That should do it. And then the 2, the last one here, is 2 times 10 to the negative 4th. So each place in our system is a power of 10. So these are the numbers you're accustomed to. Each successive place to the left is a higher power of 10, and each successive place to the right is a lower power of 10, including negatives here to the right of the decimal. So binary is similar to that, but, well, first of all, it has no decimal, so we don't deal with fractional numbers in binary, at least not typically. What you're going to have is a series of ones and zeros. So here's just an example of a binary number. And each one of these rows is going to represent a successive power of 2. So the rightmost one is going to be 1 times 2 to the 0th power. And remember, anything to the 0 power is 1. So that's 1 times 1, or 1. This next one is going to be 0 times 2 to the 1st power. Excuse me. And so this works, whatever is here times that power of 2. And this is the 0th power, the 1st, the 2nd, the 3rd, the 4th, the 5th, the 6th, and the 7th. We'll calculate this value using this. So that's 1 times 2 squared. And this next one, 0 times 2 to the 3rd. And this next one is 1 times 2 to the 4th. And this is 0 times 2 to the 5th. There we go. And this last one is 1 times 2 to the 6th power. So we can ignore the zeros because it's 0 times anything is 0. But this first one is 1 times 2 to the 0, so that's 1 times 1, or 1. This next value that's not 0 is 1 times 2 squared, which is 1 times 4, or 4. The next one that's defined is 1 times 2 to the 4th, which is 1 times 16. And the 0 doesn't change our value, but 1 times 2 to the 6th, so that's 64. So if we add all this up, that's 5 plus 16 is 21, and so that's 85 total. So this in binary means 85 in base 10, which is the number we're accustomed to. So you can encode data this way with binary numbers using only ones and zeros. And you might say, wait a dang minute, you know, this is less complicated than this. So why would I want to use ones and zeros instead of 8 and 5? Well, it's because computers only communicate with ones and zeros. You remember those electronic circuits can only be on or off. Those logic gates can only stop a signal or allow it through. So zeros and ones are all you can get with CPU architecture. So we can't use values greater than 1. So in order to encode complicated data like 85 into just zeros and ones, we have to use this binary system. So that's how you go from a binary to a real number. How would we go from a real number to a binary value, you might wonder? Well, let's do an example of that. Let's say I want to encode 116 in binary numbers. So this will be a base 10 value, and we want to convert that to some binary value. So the way we would do that is, first of all, we need to think about powers of 2. So I've got a little chart over here. I'll copy it on this page. Remember that each successive value or each successive column in binary is a higher power of 2. So 2 to the 0 equals 1. They've left that off here. So that's important to us. I'll add that. So we want to know what's the biggest number here that will divide into this? 64. So I'm going to take 64 and divide it into 116. So that's going to give us 1 here at 2 to the 6th. So 64 goes into 116 one time. And then if we subtract this away, we get 52. So 64 plus 52. So this is going to be 1 unit in the 64 column. And then what's the next biggest value that goes into it? Well, that's 32. Goes into 52. Also one time. So we're going to put a 1 here in the 2 to the 5th column. And I'll show you how to do that at the end. So we're subtracting away 32 in this case. And that's going to leave us with 20. And then we're also going to have a 1 here because 16 goes into 20. So 16 goes into 20 once, and 4 is left over. So we don't have an 8 because 8 won't go into 4. But 4 goes into 4. And then once we've done that, we have no values left over. So we're going to have a 0 for the 2's and a 0 for the 1's. So our binary number that is equivalent to 116 is 1110100. So starting from the bottom here, 1110100. That is 116 in binary. So you know how to go from binary to our number system and from our number system to binary. And again, the reason why computers exclusively communicate with binary is because the electronic architecture can only send an on or an off. It can't communicate in any more complicated way than that. So we have to break down all this complex information, like large numbers, into ones and zeros, feed that into the CPU. The CPU feeds out a string of ones and zeros that is our output, and then some software mechanism has to unencode that data into stuff we can understand. So all that's taking place in our computer. So let's think about chunks of binary data. So computers use abbreviations to describe chunks of binary data. So first of all, the simplest is a bit. That's just a single 1 or a 0. That's a single binary digit. And the one that is very rarely used, but I've heard mentioned before, is called a nibble. So a nibble is 4 bits. It doesn't even have an abbreviation because nobody ever uses it for anything. At least not in modern computers. In old computers, it was a bigger deal because the distinction between 4 and 8 bits mattered a lot. 4 and 8 bits are 4 bits are rarely used for anything nowadays, so that's not a very common term. And then byte is 8 bits. So you've heard things described in terms of bits. Those are single binary digits, and bytes, which is 8 binary digits. So 8 values. You remember when we described 116, we had to use 3, 4, 5, 6, 7 binary digits to describe it. So this is 8 binary digits that could describe values up to 2 to the 8th power. So this would have 256 possibilities. Kilobyte, that's 1024 bytes. And you might say, wait a minute, the metric prefix kilo means 1,000, and that's not 1,000 bytes. Well, you're right, but it's the closest you can get to 1,000 in powers of 2. So 2 to the 10th power is 1024, which is the closest to 1,000 you can get with powers of 2. So kilo is a bit of a misnomer here. So you can't go exactly by, the way these work in the metric system because we're dealing exclusively with powers of 2 in computer storage. So 1024 times 8 bits. So it's not just 1024 bits, it's 1024 bytes, which are 8 bits. So 1024 times 8 ones and zeros is a kilobyte, which is still a term you see. Used to be very common because most high-end computers would have memories that were measured in kilobytes back in the 80s. Nowadays, they're measured in gigabytes, and pretty soon it'll be terabytes, and so on down the line here. And that's a consequence of something I'm going to talk to you about a little later called Moore's Law, the rapid rate at which computers grow. So megabytes. Megabytes are 1,024 kilobytes. So each one is 1,024 times the other, 10 more powers of 2 times the other. So 1,024 kilobytes is a megabyte, which is 1,024 times 1,024 times 8 bits, or ones and zeros. Just out of curiosity, let's see what that is. Times 1,024 times 8. So every megabyte is 8,388,608 ones and zeros. That's a big old long list of ones and zeros. That's a megabyte. And then a gigabyte, a term we use more often with computers today, is 1,024 megabytes. And again, so 1,024 times 1,024 times 1,024 times 8 ones and zeros is a gigabyte. And then you've got a terabyte, which might be, your hard drive probably has at least a terabyte of data nowadays. That's 1,024 gigabytes, and you get the idea. Exabyte, we don't see this very often. I'm sorry, petabyte is next. Petabyte, we don't see that very often, but they do exist. So petabyte is 1,024 terabytes. And then exabyte, which would be even more unusual today, but eventually we'll get there, is 1,024 petabytes. Zettabyte is 1,024 exabytes, and a yottabyte is 1,024 zettabytes. Just out of curiosity, I'm going to look up the digital size of the Library of Congress. So it says it's about 15 terabytes. So about 15 terabytes of data is the entire Library of Congress. So think about how much a yottabyte would be. Man, you're talking about the body of human knowledge maybe, or something like that would be a yottabyte. That's just an immense size. Okay, so 32-bit and 64-bit encoding. So this basically means the biggest number the computer can understand. So you might get nowadays there's a few 34-bit computers left. Most new computers are 64-bit, but back in the old days, you even had 16-bit, and before that you had 8-bit, and so on, and 2-bit and 1-bit even, long time ago. So that's the biggest number the computer can understand. So if you have 2 to the 32, if we calculate that real quick, just a big old number. Let's see here. 4,294,000,000. So let's just say 4.3 billion. So it can understand up to number 4.3 billion. But a 64-bit computer can understand numbers all the way up to 2 to the 64th power, which is going to be way bigger. And that is, it's 1 and then 8 and 19 zeros. Gosh, so really big. So remember that billion is times 10 to the 9th, so that'll make these easier to compare, because I don't know off the top of my head the numerical term for 10 to the 19th power. Let's see. Try to make that more legible. So you've got so much bigger value here, so the computer can understand much bigger numbers, allowing the software to be more complicated and to do more interesting things. Okay, so what is hexadecimal and why is it important? Well, this goes to a fundamental difference between binary and base. So the reason, before I can explain this to you, you have to understand why base 10 is terrible at being encoded into binary or encoding binary values. So you've got powers of 10. 10 to the 0 equals 1. 10 to the 1 equals 10, and so on down the line. And then we've got that powers of 2 chart. Well, the problem is with the powers of 2, 10 is not a power of 2, and any multiple of 10 is not in this shortened list. So there's no easy way to get 2 times itself a certain number of times to relate to 10 because 10 is not on this list. So that's a big problem in converting this data. So each decimal in base 10 is about 3 1/3 binary bits. So it's not an exact number. It's bigger than 3 and less than 4. Winds up being about 3 1/3. And so this is an inexact transfer. So in order to encode binary data more efficiently, we often use what's called hexadecimal, which is similar to what we've talked about so far, but hexadecimal is base 16. So it's got 16 symbols instead of 10. So our base 10 number system has 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. Every number you can imagine is expressed using only those symbols. But with base 16, we go a little further. So you got 0, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 0, and then we go A, B, C, D, E, and F. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sorry, I put one too many. So 1, 2, 3, 4, 5, 6, 7. Oh, okay. I put 0 twice is what happened. Yeah, so F should go there. There we go. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 symbols. Then 11, 12, 13, 14, 15, 16. 16 total symbols in hexadecimal. And why is that more convenient than 10? Well, because if you see here on this list, it's exactly 4 powers of 2. So that's 5 bits. So it has 16 can be, or sorry, exactly 4 bits. So 16 can encode 4 bits of data in every one, excuse me, every one value. So for every 1 digit in hexadecimal, we can perfectly encode 4 digits in binary. All right, so let me give you an example of a hexadecimal number. These get a little more complicated, but it's kind of a fun little exercise. So let's just do a hexadecimal um, to binary example. Well, that'd probably be too complicated. Let's do the base 10 first. So we'll do 1A, B, 4. So what is that in base 10? Well, first of all, we have to remember that each of these values are powers of 16. So in the case of 4, that's not just 4, but that's 4 times 16 to the 0 power. And then the next value down is going to be not just B, but that's what B stands for. And you remember 10, 11, so B is 11 times 16 to the first power. And then A is 10 times 16 squared. And then finally, that last one is going to be 1 times 16 to the third power. So if we add all these up, into our base 10 number system, that's going to be 4 plus 11 times 16 and then down here we're going to have 10 times 256 because that's 16 squared. And then here we got 1 times 16 cubed. Let me check what that is real quick. 4,096. All right, so if we add all these up, 4 plus 11 times 16 plus 10 times 256 plus 4,096, we get 14,532. And so notice that hexadecimal is more efficient than base 10. Unlike binary, you remember it was less efficient. It took more digits to express the same value. Hexadecimal takes less because it is a bigger base. So hexadecimal is base 16, base 10 is 10. So 16 is greater than 10, meaning it's a more efficient way to store data. And you see this used with encoding binary data a lot because of that perfect relationship where 16 is a power of 2 and 4 binary digits make 1 hexadecimal digit. So that is hexadecimal. All right, Moore's Law. So Moore's Law, this is really fascinating, and implication for the future just immense. So a long time ago, there was a scientist, a computer scientist, and he observed that computers were getting faster, and they were getting faster in kind of a predictable way. So his name was Gordon Moore, and in 1965, he saw that the number of transistors per silicon chip doubles about every year. And that means the speed of the computer chip is doubling about every year and a half. And if you look at a chart for this, and I'll show you an example of a chart here. So you'll see that it is held very true over time. This is almost exactly following the prediction of Moore's Law. So that means that as time goes on, computers tend to double every year and a half. Now notice we have went from, the computing power of an earthworm's brain to a mouse's brain. And that may seem like not a big difference, but trust me, it's immense. And the implications are when just a few years from now, so somewhere before the end of this decade, maybe, we're going to achieve what Elon Musk calls the technological singularity. And that is the point where computers are smarter than humans. And you might think they already are. No, not yet. They do certain things very well, mathematics, arithmetic, and so on, but they're not quite as smart as humans, not yet. But in the next decade, they might become so if Moore's Law continues to hold. And the implications for humankind are just unbelievable. Like if you're a pessimist, you might wonder about a Terminator style future where computers decide humans are extraneous and want to kill us. Or maybe you think, you're sort of an optimist and you think computers will take care of every problem and our lives will be perfect in the future. The truth will probably lie somewhere in between, but Moore's law is a very serious, um, has some very serious consequences if it continues to hold. Computers will be better at thinking than us. It's really crazy. So one of the things that Moore's law has made possible is learning software. So this is software that learns as it goes. So it's only possible on very complicated and powerful computers, but it's basically a case where software learns from its mistakes. It tries to do a thing, uh, succeeds or fails, and then gathers data from that success or failure. And it's exactly how humans learn. When you think about it, you try to do something. If you fail, then, well, I'll try it a little different way. And then you succeed, okay, you say, yeah, that's the way I can do this. That's the way I can accomplish this task. And a good example of this is Tesla and the self-driving mechanism in Teslas. So every so often, that car will send data to Tesla's server, and Tesla's server will parse that data and use it to modify the existing code and drive a little better next time, and a little better, and a little better. And you might think, well, if it's only making little tiny increases, why is that such a big deal? Well, the difference is, unlike humans, computers can do that forever. So we make small incremental increases in our skill set, and then eventually we die, and all those skills are lost. But with software, they never die. It goes on forever and ever and gets better and better and better. So you can imagine what that means for hundreds, thousands, tens of thousands, millions of years from now. How smart the software will be. Thanks for watching. I'll see you guys next time.